A trillion messages, two live databases, and a team that decided to move every message from one to the other without ever turning the lights off. 9 days in, they're almost there. The progress bar climbs 99%, 99.9, 99.9999, and then it freezes. This is Discord. Every day, it delivers over a billion messages, and when you hit send, it just appears. No spinner, no lag. But behind that chat box is one of the largest message stores ever built. Trillions of messages, online forever. To get there, Discord didn't migrate their database once. They did it twice. MongoDB to Cassandra, Cassandra to ScyllaDB. Most engineers know that headline. Almost nobody knows how they pulled it off. The data model trick that made it possible. The shield they built in Rust to protect the database from its own users. And the afternoon hack that turned 3 months into 9 days. Let's get into it. Every database has a breaking point. For Discord on MongoDB, that number was 100 million messages. Rewind to early 2015. Discord was built in under 2 months. Speed was everything, so they put it all on MongoDB. The right call for then. Then they crossed 100 million stored messages, and the problems arrived right on cue. Here's the core of it. MongoDB leans hard on memory. The data you touch often, plus its index, is meant to live in memory because memory is fast. But memory runs out. Discord's data grew every day, and eventually the part they needed for everyday queries no longer fit. Now queries spilled to disk. Latency turned unpredictable. Open a channel and wait. It felt broken even though the servers were fine. They needed a database that could grow without falling over. Choosing a database is the easy part. The data model is where you win or lose. This is the most important idea in the video, so let's slow down. In 2017, Discord moved to Apache Cassandra. It scales by adding machines. It has no single point of failure. And it was proven at huge scale elsewhere. They started with 12 nodes holding billions of messages. Here's how Cassandra thinks. It groups data by a partition key. Everything sharing a key is stored together. So the obvious choice was to key messages by channel. One channel, all its messages in a row. And that's where the trap was hiding. A single Discord channel can live for years and never stop growing. But Cassandra struggles with giant partitions. The moment Discord imported their data, the warning started. Partitions over 100 megabytes. An oversized partition can't be spread across the cluster, and it strains the database every time it cleans up. So they cap the size. Here's the clever part. They split each channel by time into buckets. They checked their busiest channels and found that about 10 days of messages stay safely under the limit. So instead of one giant partition per channel, you get one tidy partition per channel per 10 days. 10 days. That's the whole trick. One piece left. Inside a partition, how do you order messages? In MongoDB, they sorted by creation time. But 2 messages can be created in the same instant, so that's a shaky way to tell them apart. Discord had a better tool already. Snowflake IDs, unique and ordered by time, baked right in. So every message sorts itself with no collisions. Put it together, channel bucket message ID. With those 3, Discord can jump to any moment in any channel's history. Instantly, even years back. No scanning. That quiet little bucket is the hero this whole story is built on. The scariest bugs aren't the ones that crash. They're the ones hiding in an empty room. Cassandra ran flawlessly for about 6 months. Then one day, it stopped responding. The team dug in and found one channel taking 20 full seconds to load. They traced it to a public server, the Puzzles and Dragons subreddit. Since it was public, they joined it, opened the channel to see what was so heavy, and found exactly one message inside. One message. 20 seconds. Here's the twist. In Cassandra, deleting data doesn't remove it. It leaves a marker called a tombstone. And the real cleanup happens later. Someone had deleted millions of messages from that channel, leaving just one. So every time it loaded, Cassandra waded through millions of tombstones to find that single survivor and triggered 10-second freezes across the database. The fix? Shorten how long tombstones linger and teach the code to skip empty buckets. The lesson is gold. At scale, deleted data is not free. The ghosts of messages you erased can cost more than the ones you kept. Fast forward 5 years, and the database that saved them was now waking them at 3 in the morning. By early 2022, the 12-node cluster had grown to 177 nodes, holding trillions of messages. Three problems were grinding the team down. The worst was hot partitions. In Cassandra, reads cost far more than writes. A write just drops in. A read has to go hunting. Now picture one popular channel where thousands of people read at the same moment. All that traffic slams one partition. The node falls behind, queries pile up, latency climbs. And here's why it didn't stay contained. Discord reads at quorum, meaning a read isn't done until a majority of the copies respond. So if one overloaded node is slow, every query that needs it has to wait. One hot channel, and the pain leaks across the whole cluster. The second problem was maintenance. Cassandra constantly reshuffles files on disk to keep reads fast, and Discord kept falling behind. So they ran an awkward ritual they called the gossip dance. Pull a node out of traffic, let it catch up, slot it back in, repeat. The third was garbage collection. Cassandra runs on Java, which pauses to reclaim memory at the worst moments. Sometimes, an engineer had to reboot a node by hand and nurse it back to life. In their own words, they really do not like garbage collection. What if you could keep everything you loved about Cassandra and delete the parts that hurt? That's ScyllaDB. Here's why it caught their eye. ScyllaDB speaks the same language as Cassandra. Same data model, same queries. So Discord could switch without throwing away years of design. But underneath, it's a different machine. It's written in C++, not Java. And that single choice erases a whole category of pain. Because there is no garbage collector, no surprise pauses. To engineers who'd fought those freezes for years, that sounded like a dream. It also fits modern hardware better. Instead of threads fighting over the whole machine, ScyllaDB gives each processor core its own slice of the data to own. Watch what that does. One real blocker. Discord depends on reading messages in reverse, newest first, and early on, ScyllaDB was too slow at it. So they worked with the ScyllaDB team, who made reverse reads fast, blocker gone. But the team was wise. Swapping the database alone wouldn't fix everything. Hot partitions could still happen. So before the big migration, they built a shield. Here's the part almost nobody talks about, and it might be the smartest move they made. The real enemy wasn't the database. It was concurrency. When a hot partition formed, an unlimited flood of requests piled on at once. Control that flood, and you protect the database. So they built a new layer between their main application and the databases. They call them data services, written in Rust, a language built for fast, fearless concurrency. Each one does almost nothing on purpose. No business logic. One job. Talk to the database carefully. Its killer feature is request coalescing. Picture a giant server where someone pings everyone. In the same instant, thousands of people open the app to read that one message. Normally, that's thousands of identical reads hammering one partition. A guaranteed hotspot. With coalescing, the first request starts a single worker. Every other request for that message just subscribes and waits. One database read, shared by thousands of users. Sit with that for a second. Thousands of identical requests, one trip to the database, the flood becomes a single drop. But there's a catch, and it's the detail that makes the whole thing work. Coalescing only helps if the duplicates land on the same data service. If they scatter across machines, each one fires its own query, and you're right back to a flood. So they added one more piece. They route every request by its channel. Same data service every time. Now the duplicates always meet and always collapse into one. Did this fix everything? No. They still saw hot partitions, just far less often. But it bought them the one thing they needed most: time to prepare the real migration. Now the real challenge. Every message ever sent on Discord, years of conversations, trillions of them sitting in one store. Move all of it between two live databases without anyone noticing. First, they needed storage that was fast and safe at once, so they built what they nicknamed the super disk. Use local solid-state drives for raw speed, then mirror that exact data onto a network disk for durability. Speed of local storage, safety of a backup. The new ScyllaDB cluster runs on top. Then the migration. Their first plan was careful. Write every new message to both databases at once, then slowly copy the history behind it with an off-the-shelf tool. They ran the numbers. 3 months. 3 more months of firefighting did not sound fun. So they asked a simple question. We already wrote a fast database library in Rust. What if we taught it to move data? In a single afternoon, they did. The new tool reads data in chunks, saves its place in a tiny local file so it never loses progress, then firehoses everything straight into ScyllaDB. New estimate? 9 days. So they scrapped the careful plan and moved everything at once. They turned it on. It ran at up to 3.2 million messages per second. And then remember? It froze at 99.9999%. The culprit, tombstones, again. That last chunk was packed with old, unclean tombstones, and the migrator kept timing out, trying to read through them. They cleaned up that one stubborn chunk, and seconds later, the bar hit 100%. When you get a migration this big right, the best sign is silence. They flipped the switch in May of 2022 and ran the most important test of all. They waited. The results were night and day. 177 Cassandra nodes shrank to just 72 ScyllaDB nodes. And that's not magic, it's density. ScyllaDB used about half the disk for the same data. So each node holds 9 terabytes, up from around 4. Less than half the machines, doing the same enormous job. Latency fell through the floor. Reading old messages used to swing from 40 to 125 milliseconds. On ScyllaDB, a steady 15. Writes went from a noisy 5 to 70 down to a flat 5 milliseconds. Predictable every time. And the 3 in the morning pages mostly stopped. Because the best database is a boring database. Then came the ultimate test, the 2022 World Cup final. Argentina against France. And every goal showed up live as a spike in Discord's traffic. Messi scores, the graph leaps, Mbappe answers, it leaps again. Millions of people reacting in the same instant. The exact traffic that used to mean a hot partition and a midnight phone call. This time, the database didn't even break a sweat. So how did Discord actually win? Not with one genius idea. They won by being honest about where the real problem was and fixing it at exactly the right layer. Look at the pattern. MongoDB ran out of memory, so they changed the database. The database choked on giant partitions, so they changed the data model. And that 10-day bucket carried everything after. The database got overwhelmed by its own users, so the fix wasn't even in the database. It was a shield in front of it. And a 3-month migration became 9 days, not from faster hardware, but because someone refused the obvious plan and asked, what if we built our own tool this afternoon? Maybe the most useful idea of all. Start simple but leave yourself an exit. Discord shipped on MongoDB, knowing they would outgrow it. And they did. They went from a database that woke people at night to one that quietly swallowed the World Cup final, from 100 million messages to trillions. But here's the part worth keeping long after you forget the details about Discord. Average engineers fight symptoms. Great engineers find the layer. Every hard problem lives on some layer: the hardware, the database, the data model, the code in front of it. And the whole game is refusing to fix the loudest symptom until you know which layer the real problem actually lives on. Discord didn't win because they knew Cassandra or Rust. They won because every single time they asked one question before touching anything. Not, how do I make this faster? But which layer is actually broken? So the next time something you build starts to buckle under scale, resist the first fix you see. Slow down and ask that same question. Where is the real bottleneck? And what is the right layer to fix it on? Get that right, and the fix is usually smaller than you feared. Get it wrong, and you'll be firefighting the same problem forever. Find the layer. That's the whole job. If you learned something today, you know what to do. See you in the next one.